Hi, previously I showed you how you can visualize your BAM and BET files in IGV Genomic Viewer, so you can see peaks, discrete blocks, and individual reads. But of course you would ask how I can do it more scientifically sound with proper analysis and statistics attached. Before that, let's review where all these files come from. Originally you have FASTQ, and after mapping with the star or subread you get BAM and TAB. TAB goes into the differential gene expression analysis with the RNAseq2, and traditionally you have to have at least two groups and two replicas in each. For the analysis of the ChIP-seq data, which are peaks in a genome, no attached gene names, you have to do a sort and index your BAM files with some tools, and max3. Max3 will generate BET files, and BAM and BET together can go into a Diffbind program, or BET alone can be analyzed with the BET tools. But for Diffbind, there is a more strict limitation. You need two groups at least, 3 replications in each group. And therefore my previous example where I had 4 BAM files 2 by 2 would not work. So I need a new data set. I dial mouse ChIP-seq data. Note that there is never a BAM file uploaded into Geo. These are more lightweight bigwig files which cannot be used for Diffbind. And you need at least 6 samples, so this sounds good until you check the details and see that there is no chance of using it because nothing is replicated 3 times. And then we have to continue. Let's say this one, here again, not good. After a while I found this data set where you see the replications. There are at least 2 groups, 3 replicas in each are okay. For the small data sets you can use either mouse or cell line. Don't use human data, they're highly diverse. What I will do next, I will go to SRA run selector. Then in SRA you will see this declared sample names, but also new names for FASTQ data, and then you have to be sure that you downloading right files. After download I run this line FASTQ dump all lights.1 -- faster, only faster, no qualities, because light has no qualities line, and zip them right away. Next I still have to map those faster files, and I use R-subread, mouse genome, this version, 50 base pair fragments. The script is exactly the same as I used before for human data. Map and create a counts table and BAM files. And then I'm ready for the next step. I do my sorting and indexing BAM files with the Python script. That's more or less how it looks. And also I do max, which will make BET files out of BAM files with another Python script as well. Before you try Diffbind package, you have to prepare sample table, and I use a simple trick, list my BAM files which end with by, save it to a text file, and then open it in your Excel or whatever Office spreadsheet. As an example of a sample table, you have to look into the tutorial of Diffbind, this part, and then you have to name columns exactly as they are named here. These names are reserved and not all of them are needed. In my case, I will use sample ID, then tissue for cell types, then replicate for replication, then BAM reads columns with the file names and directories included. I don't have BAM controls, and the last one will be pics for bed files. And my sample file finally looks like this: sample ID, tissue, neurons, IMOPs, replicate, BAM reads with the full directory, and pics, yes, pics with the bed files. After I did my sample file, I opened the script. Now, before Diffbind, I also call parallel library to speed up the computing. It's pretty intense in some steps than the Diffbind. So now I go to the directory of my BAM files and sample files all together. Here, yeah, samples, that's what it is. Then I read it, of course, and check whether I can read. And then I see how all those lines appearing. It means that it is well read by the program and we can move on. If you don't see this summary, it means something is wrong in your sample file and you have to correct your errors. And then check one position and it says okay. Now we can go to count reads per bed fragment. That's how it works. Default summits are 200. It means it will collect read counts in a window of 400 base pairs. This number 2 times. Depending on the computer you use, it might take quite some time. Count and analyze are the slowest steps here. Done. Then we do the next line. DBA contrast. Here you can define which column you take. You can take tissue and replicate or only tissue. I choose tissue only, single factor contrast. Then analyze. This is a slow step, probably the slowest. And then you see that it applies a blacklist immediately and uses DSEQ2 for normalization. Oh, it's pretty fast as well. So in the background it has two strategies. One is based on DSEQ2, one on HR. And so we know what it's doing. So you can also ask what focellos are. It's one contrast only. That's how samples are defined. First 3 are neurons and last 4 are IMOPs. And now we can say first output is data as there are, simply DBA report. And then we save it as a data frame. And this is the output number 1. I see the problem. Row names should be ignored. No, false. Yeah, now it's better, and it can be easily transformed into the bed file, which you can also see in IGV. Now we move to the plot, as there are suggested in the tutorial. What is strange here is that they do not split into groups by cell type. 1, 2, 3 is one category of data. 1, 2, 3. Why number 7 is here? The heat map shows that there are two groups, but unfortunately for authors, those groups are not identical to what is described in the sample file. But it explains very well why the list of differential peaks is so small in this dataset. It is 476 peaks in total, which is not much. In the case of a good clustering of samples by cell types, it will generate thousands of peaks. Next, we can do some more illustrations from the tutorial. We can do plot volcano. Yeah, okay. This is actually another heat map if you don't like additional colors this way. Then you can do other colors, and then you might think about these fancy plots which look like you can use them straight in your script, but it isn't. The description is incomplete, and when you load profile clear, you see that all the maps added to profile clear are UCSC maps. There is no entry to define which genome map you use, and therefore, since I use ensemble for mapping, I cannot use it anyway. Step number 3, annotate our differential bed file. For this I take the option which always works, unlike to some others. It works in 2 steps. So at the end you will use this annotation. At the beginning you use built-in annotation from ChipPick Anna, but it returns ensemble names. And therefore I do step number 2. I call orgmm annotation and say find me for all ensemble names the gene symbol. Okay, and then I merge all these things together, and then I also do ordering by position on the chromosomes. And so I have an ensemble name, I have a symbol, and now I have these chromosomes ordered, although not in a human order but in a computer order. Then start, end, and all details of it. And save, of course, and row names false. That's the minimum you have to do in a Diffbind protocol. To summarize my experience with the Diffbind program, it's generally okay. It does analysis in style of RNAseq. You get your output results, which is not ready to use bed file style. You have to restore strandness column and add bed file name column, then it works. But some parts of this program are a bit strange. For instance, troubleshooting is poor. You make a mistake, it tells you there is an error, but where is an error, you still have to dig yourself. For instance, if sample file is not comma separated but tab separated, it will stuck in some step, not telling you that your sample file is simply not read properly. You have to figure it out yourself. Then background control can be added to your samples, like IgG or input, but subtracting background from your BAM file counts can create a negative results, and again the program will stuck. You will be unaware where on earth this negative data are coming from. Contrasts are formally accepted, but it looks like you better stick to only single factor analysis, because more complex cases are working a bit strange, so it's hard to interpret what comes out at the end. At least for me, it was quite a puzzle. In general, visualization still needs a refinement. Diffbind results, as I said, can be converted to BET file, but all the BET files, one per each sample, is no point to show. You better take some averages per groups, and there are some simple tricks for it. The same with the bump file. Bumps are bulky, one per sample, no point of showing. It's better to convert them into a big wig, and operating with big wig is much easier. You can take averages per group, but probably next. That's it for now, and thank you. And apologies for my trembling voice. I'm a bit sick right now, and wish you good luck.